Okay guys, let's get started. Let me just wait for the video to pop up here. Whoops. And here it is. Let me just share this one here. Okay guys, live chat is on. And let's continue. We have 2 more pages left to skim through the NLLB paper. And then we can analyze the Perl scripts for processing. And after that, we can devise the processing for our text, analyze the existing baselines. So we just dig into the code and start training the thing. We already have the data prepared. We just have to pick out the high quality data sets that I know are in Serbian, Bosnian, and Croatian, so HBS. Okay, having said that, let's wrap up this analysis. We have a couple more pages left to read about how NLLB paper has trained their LID system. Okay. Performance of our LID system Flores. These numbers always seem much higher than how the actual system performs. That's crazy. Okay, let's just see what was the last sentence. Okay, despite strong results on Flores, we expect a sizable gap in performance when applying our LID model to our target web data. Indeed, various sources of noise such as language mixing, creative use of various scripts, and lead speak are widespread online. Extracting sentences from internet pages is also prone to unexpected artifacts introduced after parsing. There is no readily available evaluation set from the web domain on which to properly assess and tune performance, let alone iterate on design choices when modeling. This motivated us to audit the performance of our system with human annotators. To this end, we select 74 low-resource languages on which our preliminary LID model yield low F1 scores. After a first round of language ID on web data, we randomly selected several thousand sentences across various languages for which prediction scores fell between 50 and 90. Human annotators were tasked with inspecting and assessing. Based on these annotations, we built a challenge set for language identification to benchmark our final LID model. As shown in Table 6, we achieved lower performance than on the Flores, hinting at a non-negligible domain mismatch. They also compare against CLD3. Web corporate with extreme class imbalance. Despite the extended language coverage, our approach yields both higher F1 score at a lower FPR. We share performance of our model and CLD3 on all the selected languages in Table 15. It should be noted that since the sentences to annotate were chosen based on previous model, this challenge set is biased by that underlying intermediate model. Figure 9 brings to light a small group of confusable language pairs, Bosnian and Croatian. We work closely, because you're the same language, bro. We work closely with linguists to analyze them. Okay, impact of sentence length. As usually, more robust for longer sentences. Figure 10 gives overview. Shorter test sentences could be synthetically created from our current development samples. Okay. We could potentially augment our data as well, such that we can synthetically chop and create smaller, shorter sentences. Okay, guys, that's it. Here we can. This task is over. Completed. See how. Okay. Let's analyze the Perl scripts. We'll definitely be using heavily ChatGPT here. Just quickly open up this one. Lingual. Let me just see which one is called first. The first one to be called is remove non-printing characters. So let's analyze that one first. Here it is. Let's see this. Removes the new line character from the end of the line if present. How would one infer that from this name? CHOMP. The following commented outlines. It's almost as somebody was playing the game of how to make the worst names possible for the function that the function does. The following commented outlines show alternate ways to process the line. If this line were uncommented, it would replace all characters outside the ASCII range of 32 to 126 with a space. The C modifier at the end of the TR function inverts the character set. So it's transforming characters not in that range. Okay. Got it. And then this, if uncommented, this will replace all non-printable characters as defined by POSIX with a space. This will collapse any sequence of white space characters into a single space. This line of code replaces all Unicode control characters with a space. Fair enough. And this prints the modifier line, followed by a new line character. In summary, for the currently active code, the script reads lines from the standard input, removes the new line at the end if present, replaces all Unicode control with spaces, and then prints out the modifier line. Nice. Okay, that was easy enough. Next up, I think we have the detokenizer being called. Detokenizer. Let's try and analyze. This one is a bit longer. I'm going to try and ignore the stuff that doesn't seem super relevant, but let's kind of start attacking this code. Okay. if the language is not CS, EN, French, Italian, warning. Okay, fair enough. Let's just try and analyze this one first. The Perl code processes command line arguments are passed to script. It uses the argv array, takes the first element of the front and assigns it to the default variable. The shift function, when used without an argument, defaults to the argv array in this context. If the current argument is exactly b, it sets a special variable to 1 and goes to the next iteration. This makes the output buffer flush immediately. If the current argument is L, it takes the next argument from argv and assigns it to the language variable. If it's equal to H, then help set to 1 and go to next. In essence, the code allows the script to recognize and process various command line flags. And depending on the flag, it either sets a variable directly or shifts the next argument. Okay. And then we do this. Oh my god, this is just so cryptic. Like, whoever thought this is, I don't know, like, I don't know how people come up with ideas like this and expect this language to be ever used by broader community of people. Okay. Okay, this line checks if matches a pattern that looks like an XML or HTML tag, i.e. it starts with smaller than followed by one or more characters and ends with this. The pattern matches this criteria. Or is an empty line, or a line containing only white space characters. The pattern matches this. If either of the above is true, the line is printed as is. The comment in the code suggests that the intention is to avoid detokenizing lines that look like XML or HTML tags. Else, if this is set to true, print this, pass to the detokenized pen function. If neither of the above is met, The line is passed to the tokenized function and the result is printed. It's just so much easier when you use ChatGPT for these things. Okay, and then here is the detokenize. Let's quickly skim through the detokenize function. Where is this used? Excuse me. Let's see where this one is used. Aha. Okay, apparently in both of these two functions. Detokenize span and detokenize. Subroutine retrieves the first argument passed to the function and assigns it to the variable text. Removes the new line, adds a space at the beginning and end of text, and then this performs a global substitution on text, replacing all occurrences of the pattern space add sign hyphen add sign space with just a hyphen. Okay, and then calls the escape. And then declare is a scalar variable. Splits the text on spaces and assigns the resulting list of words or tokens to the word. To the words array. Cleared. Declares a hash and initializes it with two keys. The single quote and the double quote. Both keys have an initial value of 0. This suggests that the subroutine might be keeping track of the count or balance of quotes in the text. Okay. Prepend space. Okay, let's continue. First things first, let's understand the deescape. begins the definition, retrieves the first argument passed to the function, for each of the following lines the general pattern is pattern replacement. This uses the substitution operator to globally replace all occurrences of pattern in text with replacement. Okay. And then the first line goes like this. Replace bar with the vertical bar. Replaces the string again with the vertical bar. Replaces XML entities for the less than and greater than symbols. Legacy escape sequences for the square brackets. Replaces the XML entity for double quotes. For single quotes. Again, square brackets. The escape. Okay, this needs to be last. Okay, let's go. Let me see whether any question is there. Hi, Navjot. Hi, George. No worries. Hope you guys are enjoying it. Let me just move this and let's continue to analyze the script. So we understood that the escape remove the new line, add spaces, replace with a dash, the escape, create these variables, and then comes this huge part. Let me just see where is the end of this for loop. Here. How can you have for and then else if? This is a new one for me, guys. Only in Perl world. Let's see whether it can handle this. Of the previous detokenize subroutine. This is a long one. If ChatGPT manages to analyze this one, this is just like next level. How many characters do we have here? I'm surprised this worked because, actually that's fine. Number of words is not that big. Wow, okay. Let's go. I guess for each of the words, this means a scalar returns the number of elements. Again, whoever made the names of these functions should be like, I don't know, terrible naming. Calling a length function scalar. Okay, so then handling CJK characters. If a word starts with CJK character and it is the consecutive word, it doesn't add a space. Otherwise, prefix with space. Okay, let's ignore the CJK for now. If a word consists entirely of currency symbols or certain punctuations, it is right-shifted. Text, prepend space, words. And the text was set to what? Empty. So again, empty, prepend space, and then words. Okay. Shift them to the left. Nice, check. Handling quotation marks and similar punctuation. This logic is a bit more complex. It tries to smartly combine quotes based on the language and context. Finish. Default behavior is just prefix with a space. Okay. Fair enough. Replace multiple spaces with a single space. And this is basically strip. Let's see what this one does. This means that the sequence substitution will occur if the variable uppercase is true. Pattern matches the start of a string, 0 or more punctuation characters, or white space characters. The whole part is captured as 1 due to parentheses. And then they replace it with use conditional argument. So if this is true, this line will find the first alphabetical character in text that appears after any leading punctuation and white space and convert it to uppercase. Find the first alphabetical character. Okay. And finally, let's find this function. Yes, uppercase argument 2. Uppercase second argument. Fair enough. Okay. And finally we have, well, there is this one. And then there is the split sentences. And then we're done. Let's analyze this script. And we are done after this, guys. I sound like Darth Vader. Oh, thanks. I see now that I managed to leave my mic. Okay, can you hear me now? I sound like Darth Vader. Nice. Hopefully this is better now, guys. Let me know if not. Can somebody confirm that the sound is better now? Much better. Thanks, guys. Sorry about that. Let's see what the script does. Non-breaking prefixes. Do we have this somewhere in our code base? Probably not. What about stops? Nope. Okay. Non-breaking prefix. English language is CJK. Quiet, help, blah, 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 blah. Okay, this again handles the arguments. If L, then grab the next argument, put it to language and go to next one. If language equals Chinese or Japanese, set this one to 1, true. If prefix file not equal to empty. Otherwise, prefix file is going to be, it's going to look like this. If default to English if we don't have a language specific prefix file. Open the file, UTF-8, or die while prefix character trump. Just trying to understand the name. Let's analyze this one. I need a bit of help here. Okay. Removes the trailing new line if it exists. Checking the line content. If it's not empty and if its first character is not hashtag. Processing the line content. If item, this checks if item matches the pattern where it has some characters, followed by one or more white space characters, and then ends with the string numeric only. Okay. Just a second. And then sets this to 2, otherwise sets this to 1. The captured portion, everything before the numeric only string, is used as a key in the non-breaking prefix cache, and its value is set to 2. Lines in the file that contain numeric only at the end will have their prefix stored in the cache with a value of 2. Okay, let's go. A bit more and we are done. I'm just looking whether I can find some inspiration for processing my dataset for the LAD training in this script. So far I didn't find anything that's super useful other than just learning a bit about Perl and questioning the meaning of life after seeing some of the variable names. Okay. It prints the string p followed by a new line. If not is 0, and if the current line is empty, white space, and there is some accumulated text in text, then set it to empty. If the current line is neither an HTML or XML, it appends the line to the text variable. Okay, mostly handling XML and HTML. Okay, here's how this function works. Text markup. If text exists, then we call pre-process on the text. If markup is different than this, let's quickly analyze this line. Oops. This looks like different than binding operator. Okay, this is binding. That's why I was confused. Okay. So pre-process is the main thing. Clean up spaces at head and tail of each line, as well as any double spacing. So this is basically beginning and end. This is stripping in Python. Removes the suffix space and the prefix space if it sees the new line, and multiple spaces with a single space. Getting better at this. Sentences can start with uppercase, numbers, or Indic characters. Let's go step by step. We're almost done. Almost done. Sentences can start with uppercase letters or numbers. The code then augments the sentence start string based on the value of the language. The end result is that the sentence start contains a regular expression character class that matches characters which are permissible as sentence starters for the given language. If language equal to this one, then we additionally we concatenate this piece of this regex. Okay. Oops. . Danda and double danda. What's that? Used in Sanskrit. This comment suggests that danda and double danda are being considered as sentence split characters, are commonly used in various index scripts to denote the end of a sentence or verse. Non-period end of sentence markers followed by sentence starters. This regex identifies sequences where a non-period end of sentence punctuation is followed by one or more spaces, and then possible opening quotation marks or punctuations, or any Unicode, followed by a valid sentence starter character, as specified by sentence start. It replaces such sequences with the punctuation, a new line, and then the starting character of the next sentence. Multi-dot, followed by sentence starters, identifies sequences where multiple dots are followed by one or more spaces and then possible opening quotation marks or punctuation followed by a valid sentence starter character. It replaces such sequences similarly, adding a new line between sentences. This regex identifies sequences where a sentence ending punctuation is immediately followed by optional spaces and then quotation parenthetical closing characters, like Japanese quotes or any Unicode final punctuation, and then one or more spaces followed by. Okay. This code is defining various ways a sentence can end and then start, and it's using regular expressions to insert new lines at those points to separate the sentences. The goal is to handle both simple cases and more complex ones. So for CJK there is a special handling. For Urdu there is again special handling. Split into words. I'm not sure what this is. Maybe horizontal space. Probably horizontal space. Horizontal white space characters. Any horizontal white space. Makes sense. And then iterate through the words. Wait, where is LCF here? Uh-huh. I find this syntax super confusing. And also the indentation is confusing. Let's just paste the whole thing. Unless text already ends with the new space, append the new space. The new line, sorry. This is the last snippet we'll be analyzing. Hi Andy, thanks man. Okay, this code inspects pairs of words in a list to determine if there should be a line break indicated by the new line between them, particularly when encountering periods. It is a specialized text processing piece of code likely used for tasks such as sentence segmentation. Let's go step by step. Loop through the words. This loop runs from the first word to the second last word. Check if the current word has specific characteristics. Ends with one or more periods, may have alphanumeric dots or hyphens before the period, optionally has some punctuation before that. If this pattern is matched, the parts before the periods and the punctuation are captured into prefix and starting punct, respectively. Rules for non-breaking. If the prefix before the period is in the non-breaking prefix hash with a value of 1, and there is no starting punctuation, it won't break. Next word starts with uppercase. If a line break was determined to be needed, the new line would be added. Oh my god, ChatGPT is so fucking powerful, guys. Look at the type of analysis we've done. Like, I can't imagine how this would have looked like without having a tool like this. It's wild. Okay. And the last thing is this. Let's analyze this piece of code. processes lines of input from the standard input and applies a series of transformations, especially focusing on punctuation marks and white space. Remove the carriage returns. Remove extra spaces. Normalize Unicode punctuation, converting some special punctuation characters to their simpler ASCII, converting curly quotes to straight quotes, long dashes to simple hyphens, and the ellipses to 3 dots. French quotation mark to standard quotation mark. Certain characters in the input might be preceded by a non-breaking space, represented by this. This segment of code is adjusting or removing the spacing. Quotation styles. Depending on the language, the position of commas and periods with respect to closing quotation marks varies. In English, the comma or period often goes inside the quotation mark. Wait, handle pseudo spaces. Okay. And then decimal and thousand separators, handling the distinction between the usage of periods and commas in numbers. Wow, okay. Nice. That's all we needed, guys. Let me just turn on the light in my room, and then we are going to continue with the LID system training. Just give me a second. Okay. Nice. Let's get started. Does existing LED systems have digits in their vocab? Query that. How can I see that? Let me think for a second. Let's go to FairSec. Let me close this annoying image and analyze data. Let me open up that script. Let's go here. Okay, now let's see what this guy has to offer. So get input matrix, get input vector, get label ID, get labels, get line, get subword ID, get word ID, Okay, let's see. 1. So it has 1. Let's see whether it has this. It doesn't have 1 like this. So it definitely seems like they removed that. Let's load this one. And let's try and get word ID 1. 1. Ha! This one did not remove the words, the numbers. Okay. Well, that's all. That's the answer we wanted. OpenLID has it. The NLLB does not have it. This is maybe something worth sharing. Let me add NZ to the role. Let me open up this. Take a screenshot of this one. Okay. Let's continue. What word embedding dimensions did they use? We can again find that out fairly simply. So, okay, let's go and find a string. Okay, so let's do something like this. Get input matrix, and then just print the shape. So 256 is for the NLLB, and let's see for open LID model. Again, 256 as well. Fair enough. And they did mention that in the paper, as you can see here. NLLB did mention that. Can I also query the context length? Huh, that might be a bit more tricky. Let me see whether there are any function that might give us those results. Get analogies, get dimension. What's get dimension? Get dimension. Okay. Input matrix, input vector. Okay, let's see what else. Get label, that's not gonna be fun. Get line. What's get line? Okay. Get meter. Get nearest neighbors. Get the output. Get the output matrix. That might be fun. Get output matrix. Shape. Aha. Okay. So that tells us that we map the internal vector, which is 256, to 218 outputs. And that's the number of languages this supports. Let's see the OpenLID. 201. OpenLID supports 201. OpenLID supports 201 lengths. NLLB LID supports 118 lengths. Okay, let's go further. Get sentence vectors. Just think for a second. These models were trained. It's still not clear how we saw the skipgram model, but it's still not clear how, if you have a whole sentence, how does the system work? Like, do they take each words and then they also take their character engrams, they sum them up, but how do they combine the words before they can get the final vector that they then use to predict the output label? They probably just sum that up as well. Get sentence vector. Okay, it's always going to be 256. Get subword ID. Get subwords. I think that might be it. This is going to tell us give me some big word. Okay, here it is. Okay, let's grab the 0th value and put a string on top of it. So it looks like it's picking all of the characters from 1 through 1, 2, 3, 4, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, from 2 to 5. I think that's the same thing. The same thing was used in the NLLB model. I know that from the paper. Okay. That's additional piece of information. Get the word vector. What does that mean? Get the Word vector. Get the words. What's the length of this one? 201,110. And what about words? The same thing. So what I'm curious is, okay, I wanted to just understand a bit better how the training looks like, but we might have to go to the code to see that. Okay. With this, I think I can just grab all of this, copy, and let's create a training script. Okay. Train LID. Let me just see in stopes. Let me just find stopes and see whether they mention LID anywhere. No, they do not. But they might have it somewhere. Modules, by text, laser, evaluation, monolingual. Predict LID, what is this? See if somebody's asking questions. Nope. FT fasttext load model from the model file. predict the LID. Predict. Let's see this one. Okay, LID filter, we are using this. Okay, nothing super useful there. Let's grab this as well. Whoops. I wanted to copy paste this. Okay. This is more of an inspiration for processing. This as well. Let's understand what it does. And let's see where we have GenSim installed. Okay, this might be an issue. Let me just store this somewhere in case I start hitting some problems later. Okay. Let's see if this works. Okay, it definitely looks like it's removing. Let's understand what type of processing this is doing, because this is used for many of the LID systems I've seen people train. Okay, tokens. In tokenize. And tokenize is doing what? Let's see. So for token in tokenize, and then we pass in the doc, lower set to true, remove accents set to false, errors set to ignore. And then we go through those tokens, and if the length of the token is between the min and the max length, and it doesn't start with the underscore, in that case we save it. Okay, let's go. If lowercase or lowercase is going to be used, to Unicode, we grab text, UTF-8. If it's a string, we just return it back because it's already Unicode. If lowercase, we lower it. Otherwise, we just simple tokenize. Okay, let's see what simple tokenize does. We have a piece of text, which was lowercase. And then we have this pattern, alphabetic pattern. ChatGPT, my old friend. Designed to match sequences of words or word characters that don't begin with a digit. This is a negative look ahead. It ensures that the next character is not a digit. Matches any word character in ASCII mode. With this Unicode flag, this also includes characters that are considered word characters in Unicode, which can include letters from other languages, digits, and some other characters, like underscores. The whole construct is to ensure that each word character in the sequence is not preceded by a digit. So sequences that begin with a digit are excluded. Privyet. Privyet in Russian would also be accepted, okay, because we have Unicode flag. It can match multiple sequences with a string within a string, as long as each sequence adheres to the pattern's constraints. Let's see. Привет, мир. Hello world. Wait, but if this doesn't work, then why does this work? Wait, I think I saw some like this one. Okay, I completely misspelled it. This yields hello, and this yields world. Aha. Well, then it made a mistake up there. Oh, it did not. Oh, sorry. Well, like then here, why is world? This is preceded by a digit. Okay, yeah, it made a mistake there. But like anyhow. Hello. So basically it does what? Lower casing and then this tokenization, that's it. With a couple of these tricks. Simple pre-process. So again, it does lower casing. Converts to Unicode. Potentially removes accents and then does this simple detokenization. Okay. Let's try and train this just quickly. Let's train. Let me just see the syntax. I think this one was not using Python. Okay, train supervised. This is hierarchical softmax. We just want to use the default. Let's just see whether this will work. Let me use a simple text file, but it needs to be in this particular format. Okay, the linter is stuck. I'm gonna close down the VS Code and reopen it up. Happens every now and then on Ubuntu. Okay, here it is. It's alive again. Using the open source, it's possible to build a baseline system that is on par with the best submission. Step-for-step instructions. Lowercase, filter out the long sentences, build a language model. It's going to be mostly, I think, in C++ or C, so we won't be able to step into the code and debug. Let's just start with something and then we can iterate. So for start, let me grab a file. HPS primary. Let's grab something like Tatuiba, Serbian Cyrillic. and then copy the path. And then take maybe something like English path. Next up, we need to process those. Okay, grab the current files directory, and now we want to dump. We want to process the lines above and then dump them here. So output Serbian path is going to be exactly, and then let's analyze and similarly here English path label English Latin for file path label. Open, read the lines, so we read the lines and then exactly go through the lines, and we just add the label, we prefix it by label, and we repeat this, and then or actually I want to mix them up. Before saving this, I want to just save open the lines, something like this. And just prefix this with a label. So read the lines and then process them. Strip, add a label, and then all lines extend. Okay, at the end, randomly permute the lines. Exactly. And save the output file. And this should work, I think. And then at the end, the input is going to be precisely this. And after we've trained, we can save it. This is just a test model. Maybe we can ask like predict. Nice, that was fast. Fast as in fast text. Kick it off, let me see whether anybody's asking any questions. Good. Run. Again, let me just quickly double check that this is indeed the format. Yes. Okay. And then randomly shuffle. And then just write that to the output here. Here it is. Train the model. And it's already done. And then we save it. Oh yes, well, I could have at least printed this. Okay, we don't have to do this logic anymore. How do we load the existing model? Let me just quickly see how I do that. Model path. Exactly. Rerun. English, Serbian. Okay, nice, it works. It worked. 100% F1 score. Perfect. Okay, that's the first good step, guys. So now I'm thinking, we should just have HBS and non-HBS. That's all the labels that we need. Let's prepare that. This is fun. So let's prepare the HBS versus non-HBS. And then after we have the data, we can start iterating on the actual settings behind the train supervised. If that makes sense. Let's quickly see how the model test works. So we just pass in the file, that's it. Flores validation, eval data, Flores dev. We only have let me see what I have. Flores Flores 202. It's not matching the directory, only the files. Search files. Can we search for directories? Let's go to download. Flores should be here. Comment out all of this. Eval. Download. Here's the eval. English, Latin, Serbian, Cyrillic. That was download primary. Run. Destination path already exists. What? Can I just force it to move? Okay, then let's just delete this. Let's call this old, and this as well. And let's delete this. And let's rerun this. Let's go. Done. Copy the path. Model test. Let's go and see what we get. Zero nan. Why? Why do we get nans or Flores? What does it expect? I guess it expects the same format as always, with valid labels. Yes, sir. We passed in a bad format. So prepare validation. Something like that, and then followed by the label. Like this. Actually, it should start with a label, right? It should start with the label, and then goes the and then goes the code here, so something like this. And finally, we save that, and that's it. Read the lines, add this, right? Run the test, and all of them are perfectly predicted. Nice. Nice, okay. Well, that was not hard. Obviously, it's going to be a bit harder to get this to work on various domains, but this is a good first step. Okay, guys, a small break now. I'm going to go stretch my legs, and after the break, I want to skim again through this tutorial quickly, just to pick up some additional tricks here as well. and then we can start iterating, creating an actual data set and training our LAD system. Short break, 5 minutes, be right back. Even less. Okay guys, catch you in a couple of minutes. Okay, guys. Yes, George. Let's get back to it. Okay. Training. A couple of things we need to do. First, think of the data sources that we want to use. Second, devise the pre-processing logic. Third, figure out the hyperparameters that we want to use. And we can use Flores dev test for hyperparameter tuning. And potentially dig into the source code. So the steps are going to be choose the data sources, reprocess the data, pick the hyperparameters using Flores dev set, and then okay. So as for the data, let's think about it for a second. I think we can just use primary. Primary is cleaner than the rest, but not all of this is good. So like stuff like Bible is fine. Okay, let's just use some of the notes I made previously, manually analyzing this data. See which ones were bad. Excellent is bad, but that's the mine data. What did I say about Ubuntu? Okay. Bosnian. Don't use QED. So we won't be using the QED. And finally, Croatian. For the Croatian, don't use QED. Don't use KDE4. And don't use DGT. Okay. Let me think. How can we do this? Loop through the primary, exclude these data sets, DGT, KDE4, How big is this one? And QED. And we also have to filter them. Okay, let's quickly start like that. So copy the path to primary. Then okay, otherwise we construct the path. And then language directions that we support. All of those that have Croatian, Serbian or Bosnian. And then we'll want for the negatives to have everything else. Okay, so now that we have the data set, then we like this, and if this is in language codes, so we grab the suffix. In that case, we grab the dataset path, we connect it with this one, and then go through the files. And again, if it ends with if the target language is in allowed codes, then we go to the files, and if it ends with the target lang, in that case we create the file, we open it up, we add the label. Let's just see whether this label is good. It is. And that's it, those are the lines. Nope, we don't write immediately, we write only at the very end. And then we just say all or HBS lines. And then we just extend the lines there. And then at the very end, well, we'll first have to mix in the non-HBS data. Serbian path and English path. It's just a test. Output path is gonna be okay, later we'll figure that out. For now, let's just print what's the length of the HBS lines. Let's see how this works. Oh no, wait, I messed up here. This should be dash, not underscore. Rerun. Exactly. Open the lines, add this, and extend. And run this. And let's see how many lines we end up with. If this is at least 1,000,000, and I know it's gonna be, in that case, wow, 63 million. That's more than enough, guys. That's more than enough. Let's now just count. Labels are this is bad labels. Target lang should be the label. And let's also just keep an eye out. Let's create a counts. Counts will not be default dict of integers from collections, import default dicts, and then exactly. Rerun. Croatian has the most. $3 million there. Let me see quickly. NLLB, LID, GitHub. They mentioned somewhere. The number of lines used for each of the languages. Let's see that. No, I don't want to download it. I know I've seen it somewhere. Wait. Okay, here is a number of lines per language code. $2 million for Chinese, that's the most so far. 1 million for Uzbek, Ukrainian, Swedish, Russian 7 million, Portuguese, Polish, Dutch, Lithuanian, Hungarian. Where is German? Okay, well, German is kind of very specific. So what would be the number? What's the total number of training data? The final contains 121 millions of lines of data. before sampling. Epochs learning rate 2 to 5, only one word engram. We used our open dataset to train a fasttext LID model using the command line tool. It embeds character level engrams from the input text and then uses these as input to a multi-class linear classifier. Why do they need that many CPUs? That's kind of surprising, honestly. But we have a much simpler task. The final dataset contains we kept pre-processing minimal so that the process was as language agnostic as possible. We used the scripts writer with Moses. Okay. It would be cool if we had more Serbian Cyrillic. We should definitely subsample Croatian. Okay, so let's subsample Croatian. Let's just omit some data sets for Croatian. We don't need more than like maybe 10 million for HBS and 10 million for non-HBS. So that means let's reduce Bosnian. Let's reduce all of them to the same size as what Serbian here has, and that's enough, I think. That will give us roughly 10 million. So what I'm going to do is I'm going to randomly remove sentences. Okay, let's do that. So instead of HBS lines, let's keep Croatian lines, or let's do it like this. A list. Extend. And then for just to make sure that this worked. And then subsample. So pick. We want to have 10 million, so let's say target count can be like 3.5 million. That's it, because it's already randomly sampled, randomly permuted. Let's put this above here. So we just grab 3.5 million. And we end up with HBS lines. That's it. Let's go. How can we set the seed for random? Adam Douglas had the biggest impact in the world. Everybody uses seed 42 now. Okay, kick it off. Collect the lines. Random shuffle. That's slow. Everything works perfectly until you start scaling stuff up. As a C and C++ coder, I keep missing the semicolons. Something to get used, I guess. Nice. Hi, Apna. Yeah, I mean, I don't know, it was the same for me when I was just doing C++ and then transitioned to Python. But it's definitely like, I would say superb, because you don't need that. Like, you already tell the program by just entering a new line that you want. Like, humans know that it's a new line, why wouldn't compilers know? So why is this so slow? Well, because it has a ton of data. Maybe instead of shuffling 40 million elements in a list, we can create a random permutation. And just grab those elements. Yeah, I think this is super suboptimal. Let me just okay. Will this work? So we create a list, we permute it, and then we just grab, and then randomly shuffle. This is really slow. Luckily, we can only do it a couple of times. What's the best way to do this? I mean, okay, if this is just so slow, I can also devise a better algorithm. Like we could go and pick. Nah, this is too slow. We could just do a for loop that many times, generate a random integer from that range. Yeah. Okay. So let's do something like this. Instead of a permutation, for I in range target count, do the following. Randomly sample maybe this will be better. If we grab a random sample from this, how will this look like? So here, number of lines, and then we say, hey, from this range, sample that many elements. K unique random from population. How fast will this be? Maybe this is more optimal than the previous one. Because previously we had to shuffle again the whole thing. Now we just need to pick 3.5 million. $3.5 million elements from this range. This is just unintuitively slow. Okay. We made this a set. What's the length of this set? Just tell me it's 3.5. Okay, good. And so now we go through the permutations and we just grab them there. Okay. Same here. Number of lines. This should be much faster. Much smaller number. And we can now dump this to a file, and later we'll we'll now create the non-HBS part of the data. Okay, here it is. Why was it so slow? This is like only 3.8. I'm not sure what's dictating the speed of this one. Okay. Nice. So with these HBS lines, let's save them now. Well, we'll need to process them, obviously, but we should have done the processing here. And then we can save the file. Yeah. Okay, kind of dirty, but works. So this helps us create a HBS file. The HBS, so generate HBS train data. And next up will be to create non-HBS data. Okay guys, that's it for this stream. We've done a ton of cool work and we're getting close to just training this fasttext model. Hopefully by the end of the day I can kick off the run, and until morning maybe we can have the model ready. I'm not sure how the fasttext scales when it comes to training. The paper, the OpenLID paper, surprised me because they said they were using 76 CPUs, whereas all of the other resources I've skimmed through, it was very, very fast, like order of minutes or seconds, or depending on the size of the data, I guess. Okay guys, with that out of the way, see you in the next one. I think that's gonna be probably in 40 minutes. I'm gonna do a power nap and then I'm gonna be back to wrap this up. Okay? Cheers guys.